So in this question we are given a piece of wire of mass per unit length lambda suspended on these two wires such that it makes an angle theta because of the magnetic field pointing straight up. So the question is, if we know the mass per unit length, if we know the value of the current and the angle that the two wires make with the vertical, what is the magnitude of the magnetic field B if this thing is in equilibrium? Now, in order to solve it, we're going to have to draw another picture, and we actually have to draw a free body diagram. And the free body diagram will be drawn when we're looking from this side, okay? So, if we do that, then the wire becomes just a circle, and the direction of the current is pointing towards us. So the direction of current is going out of the board, like that. So now let's show all the forces that are acting on the wire. So clearly there has to be an mg force pulling it down. Then there is a tension force coming from the wires. So this tension force represents both tension forces of the two wires. And we also know that the tension force is at an angle theta with respect to the vertical. And there has to be also a magnetic force created by the magnetic field. So let's first find the direction of that magnetic force. Now we know that magnetic field is pointing upwards, and the current is going towards us. Now we can use the equation for the magnetic force experienced by the current carrying wire, which is equal to I L cross B. Okay, a vector product where L vector has units of length of the wire and is pointing in the direction of the current. So in this case, L is pointing out of the board. Now using the right hand rule, we can find the direction of the force FB. So index finger is the first vector, which is L. Middle finger is the second vector, which is B. It's pointing upwards. So the resultant FB will be pointing towards me in this case. So FB will be pointing this way. Okay, so from the analysis of this free body diagram, we can now deduce what is the magnitude of the magnetic field B. Well, first of all, we can see that the vertical components of tension balances mg. So we can say that mg is equal to tension times cosine theta. And on the other hand, we can say that the horizontal components of tension balances FB. So FB is equal to ILB, and I got rid of the vector sign here because we know that it's pointing this way, and we also know that L vector is perpendicular to the B vector. So sine of 90 gives us 1, so we can get rid of the vector signs and just say ILB. This is then equal to T sine theta. Let's say this is equation 1 and this is 2. If I now divide the second equation by the first one, then I get ILB over mg equals tangent theta. And so B is therefore equal to mg over IL tangent theta. And m over L gives us the mass per unit length, which is lambda. So we get lambda g over I tangent theta. And that's it.